So good afternoon. Welcome to the online course on high pressure physics. Today is the third lecture on experimental measurements. So in the last lectures, we studied how we can investigate the material under pressure using X-ray techniques, particularly X-ray reflection, then X-ray absorption, X-ray Raman scattering. In today's lecture, we will be basically basically learning how we can use optical technique to investigate material under high pressure. In this, we will study infrared absorption, Raman scattering, optical absorption, and Brillouin scattering, and probably luminescence we will skip in this lecture. So as I already mentioned, first we will start with the infrared absorption, then we will cover Raman scattering, optical absorption, and Brillouin scattering. So let's start with the main optical transition in a system. When we have a, let's say, isolated molecule or particularly molecule set of atoms. So the lowest comes when you go in terms of energy. There are several energy levels. You start with the lowest energy is let me take the pointer. Correspond to the infrared absorption. Those are the vibrational levels. Then you have an electronic level. First excited state, electronic state. You have a second electronic excited state. Now we know that the electromagnetic spectrum spans through a large range, starting from radio wave to gamma rays. And depending upon the kind of property we want to investigate, we can use different kind of electromagnetic radiation for investigation. Today we will be using the infrared and visible spectrum, UV. So if we talk about the energy levels in the system, and if we are talking about the molecule, then the lowest energy level is rotational levels. Those levels falls in the microwave region, and then you have a vibrational energy levels. These are in the infrared region, and if you further increase the energy, then these are the electronic excitations, which is in the visible and ultraviolet region. And depending upon the kind of investigation that we are interested in, we can use different kind of wavelength. This also represent basically vibrational, rotational, and electronic level in isolated molecules. So you have nuclear separation, and you have these are the electronic levels. So when you give the energy, either this rotational level or vibrational level or electronic level is excited, depending upon the energy impinge on the system. But what happens when we go to the solid? So in case of a solid, we don't have a vibration. What we have is a collective vibration of an atom that is known as a phonon. And then we can define basically this phonon in a momentum space, and then in the momentum space, this phonon has a dispersion. If you take a diatomic chain of these atoms, and then we have studied in solid state book that we can construct the dispersion relation, and this is acoustic branch. Then you have an optic branch. Now if we want to investigate this using a optical photon or light, then the dispersion of the optical light is omega is equal to ck, and this is very steep. So so the thing is, when we want to investigate this phonon with the light, the only certain phonon which satisfy these condition, energy and momentum conservation condition, they are only detected. So in case of let's say we are talking about the vibrational levels and or phonons, and then we are exciting with the optical light, then these are the modes which will interact with the photon, and we'll get this information about this one. And this is close to the k is equal to 0, which is known as gamma point. So whatever information we get in the crystal is close to gamma point. But what if your system is not crystalline? In that case, this Brilliant zone is not defined, and then we have a phonon density of state. So approximately one can construct by integrating in this axis. So you have a very sharp peak somewhere here, then you have a sharp peak, and then gradually decreasing. So when we do any optical measurement on a solid which is amorphous, what we get is the phonon density of its state, because this what do you say, the selection rule is relaxed, and because of that we can assess all the modes in the phonon density of state. Now the question comes that how we can measure these vibrational levels. So we have studied that eye infrared absorption can be used to investigate these vibrational levels, because the energy level spacing is falls in the infrared region. So in case of solid also, we can use these low energy vibration using the infrared absorption. And in case of infrared absorption, there are two techniques basically for the measurement. One can use the dispersive spectrometer, where you have a white source, then you use a grating, and then this grating disperses the white light. And then you can select a particular wavelength and then put the sample, and then whatever is the absorption is there, you get some intensity. And this is sort of a scanning type. Basically, you rotate the grating so that different wavelength is selected, and then you get an absorption spectra. But in this technique, there are several disadvantages because it takes a lot of time. The reason is only a small energy of the light source falls on the detector. And since this is the source, it is not possible to have a very bright source, so you have to integrate for some time, and then in this geometry it takes a lot of time. But there is another way or a different kind of measurement that is possible, that is a Fourier transform spectrometer. So here the time taken is very less. The reason is basically the detector receives large amount of energy, and in the spectrum in the whole energy region spectrum is recorded in a once. So how it is being done is basically you have a white light source, and then this emits a white light. Then you have a Michelson interferometer, where there is a one beam splitter. Then you have a fixed mirror and movable mirror. And then what you do is basically first you measure the source spectrum without the sample, and then you put a sample in between, and then record again this basically the interferogram, and then you can take a ratio which will give the absorption or whatever absorption that is taking place in the sample. So let's go slightly more detailed into the FTIR system. So how this works. So basically, if you have a monochromatic wave, and then this is coming this way, and then you have a partial wave reflected in this direction and this direction, and depending upon the path difference that we denote by delta, if path difference is 0, then you will get a constructive interference. And if these two rays which is coming from a different mirror doesn't have a basically same path difference, if this path difference is around lambda by 2, you will get a destructive interference, and the intensity which is reaching to detector is 0. It doesn't mean that this intensity is lost in between. What happens is this intensity goes back to the source. So you further, if you increase the retardation, then these two rays from a fixed and movable mirror, they are in phase, and then again you get a intensity at the detector. So you can represent the intensity at detector in terms of retardation delta by this expression. So here you have a delta, and it also depend upon the lambda. So 1 upon lambda 0 is nothing but nu 0 bar, which is a wave number in centimeter inverse. and we are only interested in the AC part of the spectrum. So this is the DC part we can drop. So this is important. Now when you are doing measurement, there are several factors or you can say correction factors that you have to take into account. One is the detector response. Then you have a wavelength dependent correction that comes from the reflectivity of a mirror or beam splitter, etc. So here you can include, and then finally you can sum up all these, you can add this contribution, and finally we can write the equation signal S, which is falling on the detector, is nothing but some constant which depend upon the wave number, and then of course cosine of retardation. So signal on the detector is basically Fourier cosine Fourier transform of nu 0 bar. This is for the particular wave number. But in general, what happens is you take in the commercial system, the measurement is done with the mirror having a constant velocity. So you can convert, since velocity is constant, you can convert retardation delta in terms of time. Then you can put this delta in this equation, and then you get a equation which is similar to equation cosine Fourier transform between time, and then you can compare these two equations and get what will be the Fourier frequency. So Fp is 2V prime, this one. Now let's consider, let's say we have two wavelength that is coming in the system, and when these interfere, and depending upon the retardation, because there are two frequencies, you will get a beat frequency, and this envelope gives the basically the difference in the frequency of these two wavelength. If its amplitude is different, you will get slightly different envelope. And instead of a delta function, if you have a slightly broad peak, or you can say the source is slightly broad, then what happens is, as you go away from zero path difference, the intensity decreases very rapidly. Now we will try to see in case of FT system, what will be the resolution, or what factor decide the resolution of the spectrometer. So you can take this example. So in order to determine what will be the wavelength of this coming wave, which is creating an interferogram, one need to at least record up to the first beat frequency in the interferogram, and then we can say that that can be used to calculate the wavelength of the light which is creating this interferogram. So this retardation, if you take this approximately this retardation to determine this incoming light, so that turns out to be 1 upon delta max, and this decides the resolution of the system. If let's say your incoming source is slightly broader, then it will decay rapidly, and then of course if you can basically find out the what do you say this wavelength by a smaller retardation. So the lesson we learned from this is, if we want to increase the resolution, what we have to do is we have to increase the retardation, means the total displacement of the movable mirror. And that's how you can construct, this is the similar where you have one frequency or two frequency. So in actual, you get an interferogram of this form, where this central burst point is there, and that is zero path difference. And there all the wavelengths are in phase. So that's why detector receives maximum intensity, and then it quickly decays. If your source is broader, then the decay is faster. If it is monochromatic, then you can see that decay will be slow. Now, once you have this interferogram, one can mathematically do a Fourier transform to get the spectrum. And since this signal S function, this is a symmetric, so one can integrate from to the one side and get the information. But in actual, this integration is replaced with the summation because you are recording at a finite interval. And then one can make use of a fast Fourier transform mechanism to get a spectra of this kind. Here is the optical setup of a typical FT system. So you have a light source, then you have a mirror, and then you have a basically helium neon laser is there. This laser is used for two purposes. One is basically to get the signal digitized at a particular location. So you get the interference from this laser in a sinusoidal form. So you can check the wherever zero crossing is there, and then in between these points can be interpolated and digitized, and that's how you can get the spectra. And second thing is this laser keeps this instrument always calibrated. So whatever spectrum we are getting is always calibrated in this system. So you have a interferometer, then you put a sample in between, and then you can color. So what are the main component of this FT system? So you have a source, detector, beam splitter, and optics. But the thing is, in case of FT system, there is not a one source which covers all the range. So one has to consider various sources. So like mercury source is very strong in far IR region from 10 to 500 centimeters. If one wants to do the mid IR measurement, then Globar is a better choice because it gives a higher intensity. Then if you are going in the visible, then quartz is a better. And as we learned that synchrotron emits the white light starting from infrared to X-rays, and from the optical point of view, you can consider that it gives a basically photon from far IR to UV, and then accordingly, depending upon the region, one has to select a detector like silicon photodiode in visible and UV region. PMT also can be used. Then you have in a far IR region, you have to use TGS detector, or in mid IR range, one has to use the MCT detector, and accordingly one has to select the beam splitter as well. So as I mentioned, in case of FTIR, you have several advantages over the dispersive system, like throughput is high because you are not using grating and slit, all full power of the source reach or the detector, then all wave numbers are reaching at the detector, so you have a multiplexing advantage. Because of helium neon laser, the spectra is always calibrated, and depending upon the retardation, one can get very high resolution, so one can get a good signal to noise ratio and rapid data collection. Now comes to the high pressure. When we want to do high pressure measurement, as we know that we need to focus this infrared radiation in a very small spot. So what is generally being done is one can use a optical infrared microscope where the Schwarzschild objectives are used. These are the Schwarzschild objective, and just give me one. So one can use these objectives. So the infrared source is here. Then you have a Michelson interferometer, and then this you can transport this beam into the microscope, and you can put aperture so that you can basically this will act as a secondary source so that you can focus this infrared radiation on a sample, and then whatever is transmission, that is again condensed by the Schwarzschild objective, and then finally it goes to the detector. So in this case, when we are talking about the infrared, we have to use a reflective optics. because the refractive index and transmission of a reflective optics is varies. So one has to use a reflective optics, and also we need to have a very small spot size. And when you are taking focusing using a Schwarzschild objective, your sample working distance, sample to objective working distance is very important in case of high pressure, because you need to put the sample in between these two objectives. So one need to design a very compact high pressure cell. So we have designed one very compact diamond anvil cell for this kind of measurement. And apart from this one, we learned in the first lecture that you have to select a particular diamond which doesn't have absorption in the desired energy range. So one has to use a pure diamond. If there is an impaired nitrogen impurity, it gives a strong absorption in a mid IR region. So one need to use a pure type 2A diamond for infrared measurements. And as I mentioned, the working distance is very less. So the DAC also should be very compact. The problem comes when one wants to do measurement in the far IR region. So because of the diffraction limited spot size, if one wants to measure below 10 centimeter inverse in a diamond anvil cell, then the diffraction limited spot size is very high. So you from this equation one can calculate approximately, if you are taking a 100 micrometer wavelength, which corresponds to 100 centimeter inverse energy, and then when you calculate the diffraction limited spot, it comes out to be around 150. So if you want to do below this one, it is either not possible to do the high pressure measurement, or one can use a slightly bigger diamond and do a measurement up to very low pressure. And another important point is also the numerical aperture. So when you are using a reflective objective with a diamond anvil cell which has a limited opening, then this numerical aperture also comes into the picture of deciding the diffraction limited spot. When we talk about the source, so you have a laboratory source whose flux is very high. In fact, the flux is higher than the flux of the synchrotron, but this is not important for the high pressure measurement, because in case of high pressure measurement, we are interested in the flux in a small area. So that is decided by the brilliance of the source. And if you see the brilliance of the synchrotron is much higher than the brilliance of a laboratory source. So in case of high pressure measurement, synchrotron gives a advantage, and basically if one is interested in far IR measurement, then certainly one has to use the synchrotron to get a good signal to noise ratio, because in case of normal source, what you do is basically you restrict the beam by putting a collimator, so that will reduce the flux, and then it becomes difficult to get a good signal to noise ratio in a diamond anvil cell. So as you know, this IR or any vibrational technique is very good, because the basically it provides a fingerprinting of a molecule or molecular entity. This picture gives various molecular entities which falls in at a particular wave number. So depending upon your spectra, you can check that if you are getting feature somewhere around 2000, then you can basically identify that there must be a mode from a C triple bond C and C triple bond N. So if you are getting a feature at around 3500 or so, then it's either NH and or OH will be there. So this because of the fingerprinting, one can identify what are the groups that present in your system. So let me give an example where we have done high pressure IR absorption. This is a reduced graphene oxide, which has a lot of attached groups. And when we analyze this ambient pattern, we got a basically carboxy bending group, COC, then you have alkoxy, then you have epoxy, and several other. And in this case, particularly important thing is the OH stretching mode. And if you see, these are the high pressure IR absorption spectra. And when we increase the pressure, there is a red shift in the OH stretching frequency, which suggests that there must be some extra bonding is developing with pressure, because these OH are connected to the graphene, and when you increase the pressure, the other layer comes closed, and there is that leads to basically formation of some kind of hydrogen bond, and that gives a softening in the spectra. So as we know that these vibrational levels are in the infrared region, but there are a lot of difficulties if you want to do measurement, because if you want to do measurement in a full range, then you need to change the detector, you need to change the source, you need to change the beam splitter, etc. So these measurements are quite cumbersome, and sometimes because of the symmetry also some modes are not visible in the infrared. So there is another technique which can be used to investigate these vibrational modes in the system, and that is known as the Raman spectroscopy. And both these IR and Raman gives complementary information, and this is based on the inelastic scattering of a monochromatic light, and this energy range is again the same as we get vibrational modes starting from, or you can say below 4,000 centimeter inverse. And the selection rule depends upon the molecular system which we are probing, what is its symmetry. Symmetry decide whether a particular mode will be IR active or Raman active. So if you take a simple example, if you are taking a molecule, then these are the degree of freedom. You have a 3n-6 degree of freedom for the general molecule. If it is linear, you have 3n-5 for an atom system. But what if you, when you go to the solid, then this becomes basically you need to consider the dispersion relation, and depending upon the number of atoms in the unit cell, one get a different number of branches. So if you have if your system is monoatomic or your unit cell contain only one atom, then you will get only the acoustic branch. And if you have more than one atom, then you will get optical branch 1, 2, 3. That depends. Basically, you will get a 3n total 3n modes. So 3n-3 means the 3 mode is acoustic mode. And also in the harmonic approximation, this is related to mass with this formula. So you can distinguish with the Raman or IR spectroscopy the isotope, because mass will be different. So that will lead to spectra at a different location. As I already mentioned, the activity of a particular mode depend upon the symmetry. So basically, you can consider if system is symmetric, the most likely it will be a Raman active. If it is asymmetric, then it will be a IR active. The activity of Raman or IR activity, that depends upon the polarizability. In case of Raman, it is the derived polarizability. If it is non-zero at equilibrium condition, then it will be Raman active. Now, this Raman spectra can be used to distinguish different polymorph in the system. Like you can take an example of rutile, which exists in two different polymorphs, TiO2, which exist in two different polymorphs, rutile or anatase. If you record the Raman spectra, the signature is completely different. So, with this example, what we want to say is when you are doing a high pressure measurement, if there is a structural change in the system, that will lead to the change in the vibrational spectra, because vibrational spectra depend upon the local symmetry around that particular molecule. So it is very sensitive, unlike in case of X-ray diffraction, which gives the static picture or static picture of the structure. So Raman spectroscopy is also used to find out this structural transition and the okay, and one can also guess what is happening at a particular site. Like if your starting system is four coordinated in a tetrahedral geometry, then you are getting some stretching mode. When you apply the pressure, generally what happens is there is an open space that is filled up by the rotation of these individual polyhedra, and then at a certain pressure, your system goes to higher coordination. So instead of 4, it goes to the 6 coordinated system. And if you compare the Raman spectra, then what happens is, if you are talking about, let's say, a symmetric stretch mode, so this shift to a lower energy. The reason is when the system becomes higher coordinated, the electron density is redistributed to a large number of bonds, and the bond strength of individual bond decreases, and that leads to basically shifting of this symmetric stretching in the lower side. So when you are doing Raman scattering, the biggest difficulty is the fluorescence. So when you do the Raman scattering, you get basically what you do is basically you take a monochromatic light, which is much higher energy than the vibrational energy level. So it gives basically this light gets scattered. If it comes to same vibrational level or ground state, then you get a elastically scattered light that is known as Rayleigh light. And if there is a change in the initial and final state, then you will get, let's say, if you are starting from the ground state, going to some intermediate state, and then coming to a first excited state, then you get a change in the energy of this light, and based on this change, one can find out what will be the energy difference between these vibrational levels. And if your starting state is an excited state and it comes final state is a ground state, then you get an anti-stock, and the output photon had this higher energy. But as we know, at when system is in equilibrium at any temperature, the population of ground state is more, so you get a higher intensity in case of stock compared to the anti-stock. And if this intermediate state coincide with the electronic excitation, then you will get a resonance, and the scattered intensity enhances manifold. So when you take the Raman scattering, if you have, let's say, 10 to the power 6 photon, so out of 10 to the power 6, only 10 to the power 3 photon are Rayleigh scattered, and out of these 10 to the power 3 photon, only 1 photon is Raman scattered. So you need to have a very strong monochromatic source. Fortunately, nowadays we have these lasers provide a very high flux, and then we can get Raman scattering from a large number of samples. But the problem is when you have a very large intensity of monochromatic intensity of laser, and your the energy difference is very small, then this spectra is basically, if you doesn't stop this incident laser light, then your spectra will be swamped under the tail of this light. So one need to stop this laser light. For that one uses either edge filter or notch filter, which has a rejection power of around 10 raised to power 6 at the laser wavelength, and transmission close to 90%, just uh, just close to the laser line. And depending upon the quality of these filters, one can go very close, around 10 centimeter inverse, and record these vibrational level at high pressure, which is quite difficult in case of IR, because as we mentioned that because of the diffraction limit, the spot size will be very big. So one can probe these low energy vibration using Raman scattering, and this is the schematic of any Raman scattering setup. So what you have is you have a laser that falls on basically a sample, and then this sample emits several inelastically scattered photon. This, you can say polychromatic radiation. Then you just filter the incident monochromatic light, put in the slit, and then you disperse it, and then one can record either single channel using a PMT or multi-channel. Nowadays, these CCDs are very popular, and its signal to noise ratio is also very good. So one can record these spectra. But the most of the time, problem comes from the fluorescence. When you are doing any measurement, there will be not always, but most of the time you will get a fluorescence. And this fluorescence may be because of the impurity state in between, or when you basically your energy of incident light is such that you excite it to an electronic level, then also there will be a fluorescence. So how to overcome this problem of a fluorescence? One can do a photo bleaching. Photo bleaching means there will be some attached groups to the system, which when you irradiate with the photon, they or dissociate, and this fluorescence reduces with time. That you can see in the real time when you are doing the measurement. Initially you get a more intensity, and slowly this fluorescence comes down, and then you can get a reasonably good Raman spectra. But this is always, it's not possible to photo bleach. So there is another technique. So in case of Raman, what we are measuring is we are measuring the difference from the laser line. So in case of IR, we are supplying directly the energy, and that gives the infrared absorption. In case of Raman, we are taking a difference. So our center line or zero is defined by the laser line. So, and this fluorescence line, if you see, these fluorescence line have a particular energy and the whole energy scale. So what we can do is we can use different exciting lasers, which in some case, let's say, it doesn't excite the fluorescence. So you can use the near infrared, or you can go very far from this region. If you use, let's say, UV light, then what happens is your Raman spectra will be somewhere here. So you will have a strong fluorescence, but that won't interfere with your actual spectra. So one can do the UV Raman scattering to reduce the fluorescence, or one can use infrared. If you see the scattering, light scattering is proportional to omega raised to power 4. So if you are using a lower frequency or higher wavelength, your scattering will be less, you will get a less signal. But you are using a higher frequency, your signal will be more. But the another factor is your laser power. So you can get a laser which have a high power in a visible region also. But if you are going to the UV region, then it is difficult to get a laser which has a high power in the UV region. This is a clear example where by changing the wavelength, one can get a reasonably good Raman spectra. So while recording the Raman spectra, one need to basically take care of these factors. As I already mentioned, these Raman scattering and IR are complementary, and it also depends upon the symmetry. If your system is center symmetric, then you have a basically the IR and Raman modes are mutually exclusive, or you can say the selection rule is in such a way that one mode, if it is IR active, it won't be infrared active, and vice versa. So during the high pressure measurement, if one does both kind of measurement, then one can reduce the symmetry of a system. One can also do the polarized Raman scattering, and that also gives information about the symmetry of an individual mode. So by that can be used for basically identification or mode assignment of a unknown sample. So similar to the IR measurement, when you are doing any measurement under high pressure, or not any Raman scattering measurement under high pressure, then you have several challenges. Like one need to use a diamond which is pure; it doesn't have impurities. So you can see in this graph there are two Raman spectra from a diamond. So this gives a lot of fluorescence. So this is not suitable for high pressure measurement. One need to select a diamond which has a which doesn't have impurity, and the background is very low. And another thing is, if you are doing a high pressure measurement up to very high pressure, then because of the strain in the diamond itself, one get a fluorescence, and then it becomes difficult to get a good Raman spectra. Of course, when your system is about 10 GP or so, the normal pressure transmitting medium reaches, and because of these non-hydrostatic stresses, there will be a broadening in the Raman scatter peak, and most of the time when you increase the pressure, then this intensity reduces, and also there will be a broadening, so it becomes difficult to do these measurements. So one need to design a system so that it can reject the fluorescence from nearby areas. So one need to use a very small spot size for the excitation, and also one need to have a confocal arrangement so that the fluorescence signal which is coming from around the sample, like diamond enamel cell itself or surrounding area of the sample, that can be rejected. So this is one important thing. Another thing is working distance. So working distance, or you can say the numerical aperture. So if you want to collect more data, so it is always good to have a large opening with a small working distance. Here is an example where we have studied the high pressure behavior of crystal light aluminum phosphate, and you can clearly see that when you apply a pressure, there will be a clear change in the Raman spectra. You can see here, and when you plot these Raman frequency with pressure and with the slope, one can clearly distinguish that there will be a structural transition around this pressure region, and then there will be a second structural transition. We are not going into the detail of this particular study. This is just to show that how we can use Raman scattering to distinguish structures. Next, we come to the optical absorption. Till now, we were probing vibrational mode or phonons in the system. If we want to investigate electronic excitation or electronic property of the system, then one has to use higher energy photon. Typically, this electronic excitation takes place in the UV visible spectrum. And here you see when you So basically, this when you compress system, there will be a overlap in the energy levels, and this will becomes broad. They form bands, and at equilibrium position, you will get a band and band gap. So if you want to study this band gap, like in the insulator or in particularly semiconductor, so one need to use UV visual optical absorption measurement. And when you apply the pressure, there will be a certainly change in the structure, or you can say these atoms comes close. So you have a more overlap, these orbitals overlap to a greater extent, and then there will be modification in the band structure, and that one can study using a UV visible optical absorption. And if there is a structural transition, then certainly the atomic arrangement will be different. And also there will be a change in the electronic band structure that also will be reflected if you study the band gap with the pressure. If you are talking about the semiconductors, you have a direct and indirect band gap semiconductor. So basically, the difference between these two is in one case it is there won't be a momentum transfer. In case of indirect, there will be the photon, this excitation, and also this phonon. It is mediated by the phonon, or there will be a momentum transfer. So you have a indirect band gap semiconductor. So with the optical absorption, one can distinguish these two. So how it is being done is basically you have a talk formula where what you do is first one has to do optical absorption measurement. So when you have a basically white light source, and that's source in between you put a sample. First you monochromatize, put a sample, and then you scan through the various wavelength or energy. So till its energy reaches to the band gap, you get a transmission, and then there will be a strong absorption. And based on the nature of this curve, one can deduce whether it's the direct band gap or it's an indirect band gap. This is generally done by fitting basically using this equation. If you can use this general equation where you have alpha is absorption coefficient, h nu is the energy of this photon, and then you plot with the new frequency nu. And now if this 1 by gamma is half, then you have a direct allowed transition, and if you have a 2, then you have an indirect transition. And there is much more information in this optical absorption spectra. So we are talking about when you plot this one, then you can extrapolate, and then wherever this intersect, that will give the band gap. But sometimes what happens is this curve is not a straight line, you get a tailing. And what is the origin of this tailing is basically there will be impurity state close to the band gap, or you can say when you talk about the density of electron density of state, it is not a step function, it is slowly varying. So because you are measuring basically this excitation, so if it is a smooth, then you get a smooth function. But if there is an impurity or some disorder states exist, so that will be reflected in this optical absorption curve. And one can fit this formula to find out the nature of this disorder, etc. Instead of doing a direct optical absorption, one can also do diffuse reflectance and then construct absorbance and do a similar kind of analysis. Typical optical, now we will see what will be your optical absorption setup, how what are various components. So what you have is basically you have a white light source, which gives basically photons up to a very high energy, you can say up to visible. So you have a UV visible source, that is xenon optic lamp of a high power. Then what you do is you monochromatize this using a monochromator, dispersive, and then you put a sample, and after that you put a detector depending upon the energy range. And since in case of high pressure, this signal is very weak, because these sources are quite broad. This brightness is not very high, so the total signal that falls on the detector is so very less. So one has to use a lock-in amplifier, and then one can get a reasonably good spectra. Also, one need to design optics so that the signal can be increased. Here is an example where high pressure optical measurement is performed, and then you can see that when you increase the pressure, there will be a change in the band gap. If you take this black curve is the ambient, and then when you increase this band gap reduces, you can see clearly there will be a reduction in the band gap. And if there is a sudden change in the band gap, that indicates there will be an electronic or structural transition. In this case, this band gap, you can see that it decreases, and suddenly it decreases to a lower value. And in fact, from X-ray diffraction and other technique, it was found that there is certainly structural transition in this system from C light to ferrocyanide. Next technique is the Raman scattering. Till now, we are probing if we want to probe a vibrational level, then we can use infrared absorption measurement, or we can do the Raman scattering. If we want to probe the electronic excitation, then we can do optical absorption measurement. And this technique is slightly different from those. This is used to basically reduce the elastic property of your system. You can find out the sound velocity in the system using an optical method. So let's start. So what it does is basically in the Raman scattering, the optical photons, they probe the acoustic branch. How they probe is basically you can consider that whenever there is a sound wave in a system, then there will be variation in the density in the system, and because of this variation, there will be a change in the refractive index, and when photon comes, this will basically get reflected from this sound wave, and then these waves which are going out will be one can consider that these are Doppler shifted, and because these are Doppler shifted, so certainly the energy will be different. So if one can measure the difference in this energy, so one can reduce what will be the sound velocity, and based on the sound velocity and all, one can reduce what will be the elastic constant. If you are taking a single crystal, you can measure in a different direction, in a different geometry, and you can find out a elastic constant of the system. So what the Raman scattering does is basically measures very close to can say or very low energy acoustic phonon, and this energy is less than 2 centimeter inverse or so. So you cannot use the conventional kind of a spectrometer like FT or dispersive. So this is done in a slightly different way. This is the experimental setup. So what is there is one uses basically Fourier interferometer, and since this one need to go to very close, and the discrimination required for the Raman scattering is very high. In case of Raman scattering, we mentioned we require around 10 raised to power 6 to have one Raman scatter photon. Typically, in case of Brilliant scattering, it is much higher. One require a contrast of the order of 10 raised to power 10, which is achieved by putting a Fabry-Perot interferometer in a tandem. So basically, you use two Fabry-Perot, and this beam passes 6 times, and then that gives a very high contrast, so that one can detect this change in the frequency of these photons due to the Doppler shift. And here is some more detail about this interferometer. So this is basically works on the same principle. When you have some light is passing, whenever there is a path difference is integral multiple, then you will get a basically transmission. Otherwise, it is rejected. So what one has to do is one has to change the spacing between these two mirror of Fabry-Perot interferometer. So this what you do is you put a laser light on a sample, and then you scan these mirrors so that you can get a different wavelength pass through the system. Like this one, you have a laser, you have a system, you have aperture and several things. Then this beam passes several times to this one, and now you are scanning simultaneously this. So basically, the scan gives you can say the intensity versus frequency, and the quality of the spectra depend upon the quality of this mirror that is used in the Fabry-Perot interferometer. If your that is defined by the finesse. The finesse is nothing but a separation between these two peaks, which is basically 1 lambda apart, and the width of an individual peak. So this depends upon the quality of this mirror. If these mirrors are very perfect, you get a very sharp peak, and the accuracy required is also very high, of the order of angstrom or so. This gives basically spectra. If you are taking only one spectra from one Fabry-Perot, then you have this spectra, and then second. So these are at particular angle, so they are having a slightly different path length when you scan, and then pass through these Fabry-Perot, you get a multiplication of these two, and thereby whatever signal comes, that will be very close. So this overall range is very less, around 6 centimeter inverse or so, but the discrimination is very high. And in general, this Brilliant scattering is done in various geometries, and that has a particular change in the momentum. If you are doing in a 90-degree, then this is the momentum transfer. If you are doing a back scattering, this is the momentum transfer. Here n is the refractive index. So if you are doing measurement in these two geometries, one need to know the refractive index. If you are doing a particular measurement under high pressure, then one need to find out the refractive index at those pressure conditions also. But fortunately, if you do measurement in platelet geometry, where in this case, this momentum transfer is independent of the refractive index, and one can use this to reduce elastic property without reducing the knowing the refractive index at high pressure. This is the typical high pressure Brilliant scattering spectra. So you know that just give me. Yeah, okay, here, if you see, if your system is contain a different atoms, then you have a different branch of transverse acoustic or the longitudinal acoustic. And when you are doing measurement, basically you are measuring the slope, which gives the velocity. So you will get at a different location. And here you can clearly see, this is an example where MGO is reported at 55 GPa, and you get a transverse acoustic mode as well as longitudinal. So longitudinal intensity, the energy is much higher. So you have both Stokes and anti-Stokes line, and also this D is basically the peak from the diamond. I will stop here. If there is any question, discuss. Then unmute. There is no more question. We can stop here.
Sure, I have a suggestion.
Yes.
Next talk, you might like to show.
Next talk will be by Ajay. So if something is there, we can take up in the last or something. If there is some discussion or something is there.
Basically, I want you to show the real instruments in the lab, how they look like. Though you have described all the principles involved,
Okay.
but like absorption system, how does it look really? Okay.
Okay.
If you and also IR beamline. So some of those things, it may take 5-10 minutes. You can probably come if you like, along with Ajay, and take first 10 minutes and be done with it, or at whatever stage you want. I thought people who have not Raman spectrometer, I understand many people would have seen in their labs, but other instruments like Brilliant spectrometer or light absorption or IR beamline, or even in lab FTR spectrometer, people might have not seen that.
Okay, we will include, maybe we can include those photographs in some of the coming lectures, and then we'll
Yeah.
talk.
Yeah, I mean, it's not much of work though, but I thought for completeness, we should also therefore let people know that these instruments are available in the division, and people therefore can approach one of the in charge to do some of those measurements.
Oh, sure. Yeah. So we can close this session. अभी एक मिनट में सर्च किए स्ट्रीम एंड तो